NFPA's Next Generation seminar series is a networking event for early career scholars, junior modelers, and epidemiologists working on or interested in the mathematical modeling of infectious diseases and other threats to public health. Bienvenue à tous. La série de séminaires MFPH Next Generation est un événement pour les chercheurs en début de carrière, les modélisateurs juniors, les épidémiologistes travaillant ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. So first of all, we wish to acknowledge this land on which the Fields Institute operates for thousands of years. It has been the traditional land of Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques, des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de toute Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Professor Fernando Baltazar Larios. He is a professor researcher at the Department of Mathematics of the Faculty of Sciences, National Autonomous University of Mexico, where he held his PhD in mathematical sciences with research stay at the University of Copenhagen, Denmark. His main lines of research are applied probability and statistical estimation of stochastic processes in areas such as mathematical finance, risk theory, epidemiology, and biology. Notre invité aujourd'hui est professeur Fernando Baltazar Larios. Il est professeur-chercheur au département mathématique de la Faculté des sciences de l'Université nationale autonome du Mexique, où il a obtenu son doctorat en sciences mathématiques avec un séjour de recherche à l'Université de Copenhague au Danemark. Ses principaux axes de recherche sont la probabilité appliquée et l'estimation statistique des processus stochastiques dans les domaines tels que la finance, la théorie des risques, l'épidémiologie et la biologie. Today's talk will be on maximum likelihood estimation for stochastic SEIR system with a COVID-19 application. La présentation aujourd'hui sera sur estimation du maximum de vraisemblance pour un système SEIR stochastique avec une application COVID-19. Professor, thank you for accepting our invitation, and the floor is yours. Professor Fernando? Can you? Okay.
Sorry. Thank you for the introduction, and thank you very much for the invitation. It is absolute pleasure to be here. Okay, today I will present a stochastic version of the SEIR model. It's maximum likelihood estimator for some parameters and an application of this model to COVID-19 with data from Mexico City. This is based on a joint work with Francisco Delgado Vences and Saúl Díaz Infante. Ready. This is the structure for today. First, I will present the motivation of some motivation for the work, the conclusion, and some previous works. After, I will present the version of the stochastic model that we studied. First, the deterministic version, after the corresponding stochastic version. In the third section, I will talk about a method for obtaining estimators of some crucial parameters and their properties. Here in simulation study section, I will present a simulation study to calibrate the method. And finally, I will show a fit of this model to data from COVID-19. Okay, I want to start giving some motivation for develop the version of the stochastic SEIR model presented in this talk. Parameter calibration of epidemiological models with data is a demanded but crucial task. The current COVID or the past COVID pandemic has revealed the complexity and developing epidemic data-driven models. Models based on stochastic differential equation for study the behavior of disease have the advantage of characterizing the central tendencies, and this capture in their formulation the random variability of the data, and therefore quantify the uncertainty that is naturally related to the parameters or phenomena. On the other hand, when you have epidemic stochastic models based on the stochastic differential equation, in general, it's noisy, have good estimators for its parameters. So we want an epidemic stochastic model based on the stochastic differential equation, so that we can obtain its good estimators and fit this to real data from COVID-19. What about the contribution? We first took a deterministic SEIR model, perturbed this, and obtained the corresponding stochastic version. After we developed a good estimation of the model for some crucial parameters, the next step is we illustrate our methodology by simulation, and finally we calibrate the stochastic version model with the data of symptomatic, reported, and confirmed cases in the Mexico City. Okay, there are previous works that consider epidemic stochastic model based on the stochastic differential equation. In particular, there are works that report estimation for models, but using a more simpler structure. For example, the SEIR model, and with only present numerical experiments of synthetic nature. Complex stochastic models, similar to the one considered here, that only studied the theoretical basis of present numerical simulation, but without estimation methods. And words about the SEIR model, for example, sorry, give me a moment. For example, Gangusa focus on the calibration parameters by adaptative MCMC and extended Kalman filter method. Jota report other Bayesian techniques. Rios Gutierrez applied the maximum likelihood method. And finally, Otunaga reports parameters estimation with local methods of moments, but all these works is for different versions of the same model considered here. Okay, now I present the version of stochastic SEIR model. We use a common deterministic structure that has been applied for COVID-19. Our formulation splits the according to the following compartments. The first compartment is subtitled the class S. This compartment denotes the population members on the risk of contagious. The next class is the exposed. Members of this class come from the S class and represent the population fraction that hosts but cannot transmit the virus. And after a period of days or time period, these people develop the faculty to spread this virus and became infected. Asymptomatic infected class. In this class, denote the population fraction that spreads the virus, but these guys not develop symptoms or maybe mild symptoms. Symptomatic infected, this represents the COVID-19 reported and confirmed cases that develop symptoms. The recovery class, in this class, after a period of time, a member of the infected class entered to this compartment and to become recovered and immune. And finally, the D class, death. Here we count the cases that died to COVID-19. Okay, with this compartment, we obtain the following deterministic system of equations, where mu is represent the natural death and birth rate. Beta S is the symptomatic infection rate. Beta A is the symptomatic infection rate. Kappa is here, and is the transfer rate from the exposed class to the infected stage. And P is the proportion of asymptomatic individuals. Obviously, 1 minus P is the proportion of symptomatic individuals. Theta is the proportion of symptomatic individuals who died by the virus. Alpha A is the symptomatic recovery rate, and alpha S is the, alpha A is the asymptomatic recovery rate, and alpha S is the corresponding symptomatic recovery rate. And finally, gamma is the desired immunity rate. And this is the deterministic system following the description of the compartments in the past section. Now I present the parametric estimation for this case using a Bayesian propose. In this case, and in the stochastic case too, we only focus on estimate the 3 parameters: P, the proportion of asymptomatic people, beta A and beta S, the infection rates. To calibrate parameters of this deterministic base, we deploy an MCMC by counting the cumulative incidence of new infected and reported symptomatic cases. And we denote by XT this cumulative incidence at time t, and suppose that its profile follows a Poisson lambda t with mean lambda t, and following the ideas of Acuña and Segarra, we propose the priors for P and betas, and count the cumulative report confirmed cases in the Mexico City with this size of population. The Bayesian estimation results in these values, and now I present the estimation. You remember that I only estimate the betas and the P. The other parameters, we took this of this work. Okay, now we take the deterministic model and perturb the natural death rate and obtain the stochastic version. There are many words about the epidemic modeling with stochastic differential equations that perturbs the infection rate, but we proceed in different directions because we want deduce the estimator for the infection rates by maximizing the underlying likelihood, and we need a tractable form for the diffusion, for the likelihood function. We perturb the natural rate because the role of this parameter is particularly important with the demographic process, as birth of death are significant. It is well known that the introduction of a new mortal and contagious disease modifies these processes. But when the disease is in the starting phase, these demographic processes tend to experimental small fluctuations. And with this, we can propose the following hypothesis. The number of deaths in the context of the regarding pandemic can be estimated as random fluctuations of the natural death rate. Then we describe this fluctuation with the inclusion of the conveniently stochastic processes. For my objective, we see it as a good idea the perturbation with a standard winner processes. And with this approach, we obtain an tractable stochastic formulation to deduce the explicit estimators for the parameters of interest, betas, and p. Then we perturb the natural mortality rate mu by a standard binary process WT with noise intensity sigma, and we obtain the follow stochastic system where we normalize with respect to the size of population n and obtain this system. Is the system or the version, the stochastic version based on the previous deterministic system. What about the advantage of this version? First, we know that because the model couples mortality rate mu in all compartments, this perturbation implicitly captures random fluctuations from all compartments. And second, this particular forms allows us to deduce a closed form for the underlying likelihood function and modulate variance of the solution by the noise intensity. And finally, there are existence and uniqueness of the solution in a compact time interval from 0 to t under some conditions on the coefficients of the each stochastic differential equation component. Okay, now I will present the statistical inference. First, I describe the methodology. First, we assume that the true values of the parameters of interest, in this case, 4 parameters, betas, p, and the noise, sigma, are constant, but to estimate the parameters of the function, sigma, we can use the quadratic variation over time interval of the processes of system of stochastic differential equations. After, by applying Lampert's transformation to each component, we can rewrite the stochastic differential equation as a system where all the function parameters are 1, and we can apply the Girs-Anot formula for the new system, and we can obtain the likelihood function and the corresponding maximum likelihood estimation for the rest of parameters, betas and p. To estimate the parameters of the function, we can use the quadratic variation over time intervals from 0 to t of the process of the system of the stochastic differential equation. In this case, the quadratic variation over 0t is denoted by this notation. Sorry, I can mark. Okay, no problem. And this is the with this expression we can obtain the estimation for the diffusion parameter, and by maximizing the log likelihood with respect the corresponding beta, we have the following maximum likelihood estimator, and we can observe that these parameters depend on the diffusion parameter and observation of all classes of the population. And now the similar form, by maximizing the log likelihood with respect to P, we have the corresponding maximum likelihood estimation for P. The corresponding estimator is this, and in this case we can observe that this parameter dependent on the diffusion parameter and observation of all classes of the population and the other parameters of system, in particular the parameter kappa, remember, is the transfer rate. Now, to prove consistency and asymptotic normality of the maximum likelihood parameters, we will make the following hypothesis. And this hypothesis, in other words, give me the conditions to estimate parameters in a ground phase of the outbreak. Under these conditions, the S class, the S population, the susceptible population, decrease while the exposed and infected classes are in the ground phase. And now, under this hypothesis, we obtain the following theorem. We have a consistency result of the maximum likelihood estimation. If you want, you can see the details of the proof of this theorem in this work, this paper. Okay, now I present the calibration of the method, and for this, we use the Milstein method to generate paths of processes of the stochastic system in a time interval 0t, and we apply the expression of the previous section to estimate first bit sigma, and after the corresponding maximum likelihood estimation for betas and P. Then, using the Milstein method, we divide the interval from 0 to 10, in this case, T, into n subintervals of the same length, and we obtain the observation of each process at the same times. And using these parameters, we simulate 1,000 data sets in the interval from 0 to 1, and we use these values for betas, P, sigma, and this discretization. And for the other parameters, we use the values of the deterministic version in the past table. Okay, the average of these data sets and the corresponding standard deviation are present in this table. We can see that we have a good estimation, and this estimation have a small standard deviation. Now, I present the application to real data. I start with a data description. For the data description, we use the data set of new symptomatic and confirmed COVID-19 reported cases daily in Mexico City, considering that population is this population. It was the population on March 10, 2020. The pandemic started in Mexico. The dataset contains 47 records in the period from March 10 to April 25 of 2020, and we use these records denoted by an ISO to construct the observation of the process infected, symptomatic infected, and combining this observation and the Milstein method, we can generate the other 4 processes of the system with the parameters of table 1. Table 1 is the parameters of the deterministic case. Sigma, this value for sigma, and this discretization. We use this algorithm to generate the data set for the other 4 processes. In step 1, we need to choose the initial values of the other 4 compartments, and we use we took the first 2 classes of the deterministic case, E and IA, and the symptomatic infection. In this case, 74 is the number of symptomatic and confirmed COVID-19 report in Mexico City on March 10. And I take the recovered 0 people, and the complement is the susceptible. And we in the step 2, we generate the Brownian increment, and using the parameters of the deterministic model and the observed symptomatic class, we generate the other 4 classes with the step using the step from the step 3 to step 6 until have the 47 record for the 5 classes. Okay. Then, using the described methodology in the previous algorithm to generate the data and apply the expression corresponding, we can calculate the estimation for sigma, betas, and p, and this is the results. And we generate and repeat 1,000 times, and we obtain 1,000 data sets using the data of Mexico City, and in this table gives the average of the estimators and the corresponding 95 confidence interval. Now I present the evidence. This works well. This figure shows the average and the 19.5 confidence interval of the 1,000 pounds of the cumulative new symptomatic and confirmed COVID-19 reports case from Mexico City. We can note that the new estimation followed the GIT data profile in the closer way than the corresponding Bayesian calibration. This is the comparison in between the Bayesian. Bayesian is for the deterministic case, and MCMC is for maximum likelihood estimation is for the stochastic version. And further, all observation drop in the corresponding confidence interval only for the maximum likelihood. And this suggests that this proposed methodology and the stochastic extension improves the Bayesian fit for this data set. And finally, I present the validation of the model. To validate the stochastic model, we compute the residuals corresponding to data or reported and confirmed COVID-19. The objective is to show that the residuals are Gaussians. If this is the case, then the noise W in the stochastic model will be consistent with the Brownian motion, and we can conclude that the residuals are Gaussian, so the model fits well. This is the cuckoo plot, the theoretical quantile versus sample quantile, and the result is, and we can model fits well. And that's all. Thank you very much.
Thank you very much, Professor, for this great talk. And it's time for the questions. I think there was a question from Mohammed Khalifi about what is your time unit that you used. A question in the chat.
Yeah, I mean, I was actually asking about
the time unit is a day. For the real data, we use the have records for day by day.
Okay. So is there any other question? Okay. I have a question about stochastic. There is a part of stochastic modeling with Markov chain regime switching. So I don't know if you have experience with the estimation of such as model. Do you have any comments on how to deal with those type of stochastic differential equations with the regime switching?
I only work with the stochastic differential equation with the random effects. Is some similar, but no specific with the switch or Markov and Haydn models. But it's more complicated. But we need to use another techniques, for example, the EM algorithm, or maybe Bayesian techniques.
So I think there is another question from Mohammed Khalifi.
Yeah. So can you please reshare again your presentations, the slides?
Yeah.
And it would be nice if you go back to the first estimation algorithm. I mean, where you
the deterministic case.
Yeah, not that case, but the Bison case, where you put some assumptions on the incidence, and just go back a few slides ago. Okay.
Here?
No, but go back, please.
You tell me where?
Just go back. I will stop you when you reach. Yeah, here.
Okay.
So so I'm just wondering, here you have X is the incidence.
Yeah.
And It's I mean, yeah, it's Poissonian distributed with the mean lambda t, and here you have lambda t. You are just integrating 1 minus p. You know, is that the probability of an exposed individual to be symptomatic, isn't it? So this means that this lambda, you are just assuming, correct me if I'm wrong, but what I see here is that you are just assuming that only symptomatic individuals who are responsible in generating new infections. So what about the others, the asymptomatic individuals? And we know that, you know, for COVID-19, there is a, I mean, we have a long it's hard to say if it's a big portion of new infections become pre-symptomatic before even developing or show symptoms, but also we have another part of asymptomatic infections. So it's hard to neglect their effects or their contribution in generating new infections.
Yeah, I agree, but this consider the previous wars, and I don't sure if your propose is better, but I don't have arguments to defend this, but I agree. This prior sounds very large for the asymptomatic people, but we only take the previous wars based on the records of Mexico City.
Yeah, I mean, yeah, you can just maybe modify your assumption slightly by including also asymptomatic individuals. And it would be better if you extend your model to have like a pre-symptomatic phase. So that would be also interesting. Also, this assumption of uniform probability of being asymptomatic, you know, if you have, for instance, like a population of 100 people put within a closed room or a closed space, and you have enough resources to track their prevalence situation at the time, you can realize who is and what is the proportion of asymptomatic individuals. And yet, but now we have no, I mean, we have a lot of uncertainty about the parameters. So I was also looking forward to see how much the uncertainty that you will get about P, but it looks like, I mean, you have it looks like quite narrow the standard, the interval. I mean, just the word interval for your estimation of P. So that's I mean, that would be interesting to.
It's very good observation. Thank you.
Well, thank you, Mohammed. Is there any other question? So I have a question regarding if you have, in case you have data with jumps, and how can you fit those type of data to an epidemic model of, or any type of model with such kind of data? How can you detect those jumps in order to fit them to the model?
The jumps, maybe you talking about the stochastic differential equation with jumps. It's possible. I have some words about the inference, stochastic inference for this kind of processes, but not in using this type of data. I only work in the for the price of the stocks.
Okay, that's good. So maybe it will be agreed for extension for to
Yeah.
this. Yeah,
It's a good idea. Thank you.
thank you. Is there any other question? If there isn't, thank you very much, Professor, for this great talk. And it was nice to see such estimation for the stochastic differential equations. That's a great field to work on, and also as an application for epidemiology, it's great.